Imagine you're floating outside the International Space Station. No walls, no floor, just you, a suit, and the whole universe stretched out in every direction. Earth curves below you in blues and whites you've never seen in a photograph. The silence is total. For a moment, it feels peaceful. Then your suit fails. Not dramatically, no explosion, no warning alarm, just gone. And what happens next isn't what most people expect. You don't freeze instantly. You don't explode. You don't drift away peacefully like the movies suggest. Your body begins a process so specific, so systematic, and so irreversible that scientists can map it almost minute by minute. Within seconds, things go wrong. Within minutes, they cannot be undone. Within 1 hour, the question isn't whether you survived. It's what exactly is left. This video will walk through what deep space actually does to the human body. Not in theory, not in science fiction, but in the precise biological and physical sequence that would unfold if you were exposed to it right now. The answer is worse than you think, and more specific than most people ever hear. Before your body fails, you need to understand what it's failing against. Because most people picture space as cold and empty. That's true, but it's not the whole problem. Space is not just the absence of air. It's the absence of pressure, of protection, of almost everything your biology was built to rely on. The vacuum of deep space sits at roughly minus 270 degrees Celsius in the shade. That's 3 degrees above absolute zero, the coldest temperature physically possible in the universe. In sunlight, exposed surfaces can swing to over 120 degrees Celsius, not gradually, instantly, depending on which side faces the sun. Your body was designed to operate in a narrow band, roughly 36 to 37 degrees Celsius internally. Space doesn't negotiate that range. Then there's the pressure. At sea level, Earth pushes about 101,000 pascals of atmospheric pressure against every centimeter of your skin. You've never noticed it because it's always been there. The moment that pressure disappears, your body doesn't know what to do. It was never designed to function without it. Think of a sealed soda bottle. On Earth, the pressure inside and outside is balanced. Take it to the vacuum of space, and the bottle doesn't just open, it ruptures. You are the bottle. And then there's radiation. Deep space is threaded with high-energy particles from the sun, from dying stars, from sources we still don't fully understand. Earth's magnetic field blocks most of it. Out there, nothing does. You're not floating in emptiness. You're floating inside a silent machine designed to take you apart. Most people assume the vacuum kills you immediately. It doesn't. That's almost worse, because the first few seconds feel survivable. Your body doesn't shut down all at once. It begins a sequence, and that sequence is precise enough to follow like a clock. The moment pressure disappears, the oxygen already in your lungs becomes useless, not because it vanishes, but because without atmospheric pressure, your lungs can't transfer it into your blood. You can hold your breath all you want. It won't help. In fact, holding your breath in a vacuum is dangerous. The gas inside your lungs expands as external pressure drops. Hold it long enough, and you rupture the tissue. The correct instinct, exhale immediately, and is also the one that leaves you with nothing left. Within 9 to 12 seconds, the oxygen remaining in your bloodstream runs out. Your brain is the first to notice. You lose peripheral vision first. Then your field of view narrows like someone slowly closing a curtain. By the 15-second mark, most people lose consciousness. Not dramatically. You don't feel yourself go. One moment you're aware, then you're not. This is actually the merciful part of the timeline, because what happens to your body after you lose consciousness doesn't require your awareness to continue. It just continues. Your skin and soft tissue begin to swell, not catastrophically. Your skin is elastic enough to hold, but the swelling is real, measurable, and deeply wrong. Saliva on your tongue starts to boil, not from heat, from the absence of pressure. At low enough pressure, water boils at body temperature. Your mouth is warm enough. The vacuum does the rest. You're unconscious by the time this happens. But it's happening. The clock has started, and it doesn't stop while you're asleep. Here's the part most survival discussions skip, because the vacuum is dramatic. The radiation is invisible, and in some ways far more permanent. Deep space is saturated with ionizing radiation. That's high-energy particles moving fast enough to pass straight through your body and rewrite what they find inside. Not burn it, not bruise it, rewrite it. When a cosmic ray particle hits a strand of your DNA, it doesn't destroy the cell outright. It damages the instruction set. Sometimes the cell repairs itself correctly. Sometimes it repairs itself wrong. Sometimes it doesn't repair at all and starts copying the error. That last option is how cancer begins. On Earth, your body handles a manageable level of this constantly. The atmosphere absorbs the worst of it. Your DNA repair mechanisms handle the rest. In deep space, the dose rate is roughly 300 times higher than what you'd receive on Earth's surface. In a single day of unprotected exposure, you'd absorb more radiation than most nuclear industry workers are permitted in an entire year. That's one day. Now consider the timeline we're discussing, 1 hour. In 60 minutes of unprotected deep space exposure, the radiation damage accumulating in your cells is enough to measurably raise your lifetime cancer risk. You wouldn't feel it. No heat, no tingling, no warning. Your body would register nothing unusual while the damage compiles at the molecular level. This is the cruelest part of radiation. It doesn't announce itself. It invoices you later. And there's a second layer, solar particle events. Sudden eruptions from the sun that can spike radiation levels by a factor of hundreds within minutes. No suit currently in existence fully blocks a major solar particle event. You'd have perhaps 15 minutes of warning. If you're already unconscious, which at this point in the timeline you are, you get no warning at all. The radiation doesn't need you to be awake. It was never waiting for your permission. Your blood has been quietly failing since the first second. By this point in the timeline, the process has a name: embolism. It sounds clinical. What it describes is not. Embolism is what happens when the pressure around your body drops so low that the dissolved gases in your blood, nitrogen, oxygen, carbon dioxide, begin to form bubbles. Not in your lungs, in your veins. Think of a can of carbonated water. While it's sealed, the gas stays dissolved, invisible, harmless. The moment you release the pressure, it comes out of solution. Your bloodstream is the can. The vacuum is what opens it. These bubbles don't stay in one place. They travel. They block circulation. They expand inside vessels that were never designed to hold gas. The medical term for what follows is gas embolism. The practical consequence is that your cardiovascular system begins to lose the ability to do its only job. Your heart keeps beating, for a while. It's a muscle. It doesn't need conscious instruction. But it's pumping a mixture that can no longer carry oxygen effectively. The organs that depend on oxygen most begin to fail in sequence. The brain first, already unconscious, now deteriorating. The kidneys next, then the liver. Each one shutting down not because it was damaged directly, but because the delivery system stopped working. There's a grim irony here. Your heart, trying to keep you alive, is actively circulating the damage. Every beat moves the bubbles further into territory they shouldn't reach. Rescue teams have a concept called the golden hour. The idea that if trauma victims receive advanced care within 60 minutes, survival rates improve dramatically. In deep space, unprotected, your golden hour is spent becoming unrescuable. Not because rescue is impossible, because by the time 60 minutes have passed, the cascade of failures has compounded past the point where returning circulation solves anything. The bubbles are there, the damage is mapped into your tissue, the organs have crossed their own individual points of no return. Your heart is still beating. That's the worst part. It just isn't saving you anymore. Everyone assumes the cold kills you first. It doesn't. And understanding why makes the situation considerably darker. Heat doesn't leave your body the way most people imagine. On Earth, cold air pulls warmth away from your skin through conduction, direct contact between your body and the surrounding medium. Space has no medium. There's nothing to conduct into. The only way your body loses heat in a vacuum is through thermal radiation, your body emitting infrared energy outward into nothing. That process is slow, slower than you want it to be. It would take anywhere from 12 to 26 hours for your body to cool to the temperature of deep space, depending on your position relative to the sun. That sounds like a relief. It isn't, because you're not waiting comfortably. Every other system in your body is failing on a much faster timeline. The cold isn't coming to save you from the other damage. It's just arriving late to something that's already finished. If you're in direct sunlight, the situation reverses. Exposed skin facing the sun absorbs radiation at temperatures exceeding 120 degrees Celsius. The side of your body facing away simultaneously sits near absolute zero. Your body becomes a study in thermal extremes, one half cooking, one half approaching the coldest possible temperature, simultaneously, with no ability to regulate either. Your internal temperature regulation, One of the most sophisticated systems your body runs automatically becomes completely irrelevant. It's still running. It just has nothing it can do. Think of a thermostat trying to heat a building with no walls. The system functions perfectly. The environment simply doesn't allow it to matter. There's a version of this that's easy to romanticize. Drifting, quiet, cold, and still. But the sequence we've tracked, the ableism, the organ failure, the radiation accumulating in your DNA, none of that is quiet. It's just invisible. The cold that everyone fears is the last thing to arrive. By then, it's a formality. Let's say rescue arrives. A ship, a team, someone who knows exactly what to do. Let's say they reach you within the hour. Here's what they find. You've been unconscious for roughly 45 minutes. Your cardiovascular system has been circulating gas bubbles through your organs for nearly as long. Your brain has been without functional oxygen delivery long enough that cellular death, not damaged death, has occurred in measurable regions. Your skin is swollen. Your core temperature has begun to drop, slowly, but the internal environment has already shifted past thresholds that matter. And your DNA carries radiation damage that no surgery addresses, no procedure reverses, no amount of time in a hyperbaric chamber undoes. The rescue team can restore pressure. They can restore oxygen. They can get your heart beating with full circulation again, but they cannot unboil the gas from your blood vessels. They cannot restore the neurons that died during the window of oxygen deprivation. They cannot reach into your cells and correct the ionized strands of DNA that are already copied, already propagating. Medicine has a word for this: sequelae, the damage that persists after the primary event ends. In most trauma, sequelae are manageable. A broken bone heals, a wound closes. In unprotected deep space exposure beyond the 15-minute mark, the sequelae aren't complications. They are the outcome. The 15-minute threshold isn't arbitrary. Animal studies and modeled human exposure data both point to the same conclusion. Beyond roughly 12 to 15 minutes of unprotected vacuum exposure, the probability of neurological recovery drops toward zero, not toward low, toward zero. Rescue after 60 minutes isn't rescue. It's recovery of a body. And this is the part that deserves a moment of stillness. Physics. Set the clock before you arrived. Physics set the clock before you arrived. There's something worth sitting with at the end of all this. Not a lesson, not a warning, just an observation. The human body is, by almost any measure, an extraordinary piece of engineering. It regulates temperature across seasons. It repairs DNA damage thousands of times per day. It maintains pressure, circulation, and chemistry simultaneously, automatically, without a single conscious instruction from you. You have never once told your heart to beat. It has beaten over 2 billion times anyway. And yet, take that same body, that self-regulating, self-repairing, damage-tolerant system, and move it 200 miles straight up. It survives for 15 seconds of awareness. Perhaps 12 to 15 minutes before the damage becomes irreversible. 1 hour before the question of survival becomes purely academic. 200 miles, the distance from Lahore to Islamabad. A drive you could make in 2 hours on a clear road. That's the margin between the environment your body mastered over millions of years of evolution and the environment that dismantles it faster than medicine can respond. We tend to think of space exploration as a story of human expansion, of pushing boundaries outward. But the biology tells a quieter story. The boundary was always there. We didn't push past it. We built machines, suits, capsules, stations, thin shells of engineered atmosphere, and we carried our boundary with us. Remove the shell and the boundary snaps back instantly. There is no version of the human body that survives deep space. Not yet. Possibly not ever in its current form. Every astronaut who has looked out at the universe has done so through several inches of engineered protection standing between their biology and an environment that would end it in minutes. That's not a failure of ambition. It's an honest measurement of where we are. We are a species that looks out at a universe we cannot survive and goes anyway. The shells we build are getting better. The universe hasn't changed at all.